So question 5 says that the Earth with a mass of 5.9 times 10 to the 24 kilograms rotates around the sun in an orbit that is about a circle with a radius of 1.5 times 10 to 11 meters. So the first thing it asks just is for the orbital speed of the Earth around the sun. So if our sun is here at the center, and then our Earth is here, rotating about the sun. Okay. The radius here, it says, is 1.5 times 10 to the 11 meters. And so first, just find orbital speed. So to do that, that's just understanding that speed is going to be distance over time. And my distance is going to be my circumference divided by my time. That's going to be 2 pi r divided by my time. So that is 2 pi times 1.5 times 10 to the 11 meters divided by, let's just say 365 days. When I do that, that's going to give me a speed of 2.58 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 to the 9 meters per year. And so what we need to do then is let's just get this into SI units. So we'll go to meters per second. And so what we'll do is we'll say 1 year is equal to, that's meters per day. Sorry, we did divided by 365. So meters per day. So we'll say 1 day is equal to 24 hours. And we'll say 1 hour is equal to 60 minutes. And 1 minute is equal to 60 seconds. And so we'll take this value here, divided by 24, divided by 60, divided by 60, and we'll get our value in meters per second. And when I do that, I get 2.98, or 99 really, times 10 to the 1, 2, 3, 4, times 10 to the 4 meters per second. So that's how fast we're traveling throughout space in meters per second. Second part of the question says find the centripetal acceleration experience of the Earth. And then we're going to find the magnitude of the gravitational force exerted on the Earth by the sun. So, second part is B, find centripetal acceleration. So that's going to be acceleration centripetal is simply v squared over r. So that's going to be 2.99 times 10 to the 4 divided by 1.5 times 10 to the 11, and this is a squared value. Now when we plug that in, we're going to get an acceleration of 0.0059 meters per second squared. And so if we think about that, the acceleration we experience around the sun is incredibly small. Compare that to the acceleration we experience on Earth of g equal to 10, right? So this is orders of magnitude smaller. So this is why we really don't feel that pull towards the sun, because the acceleration towards the Earth is just substantially greater than that towards the sun. So lastly then, we're going to find force of gravity by the sun. And again, if we think about this, if this is our sun and then this is our Earth, right, we have a velocity tangential there, and then we're going to have a gravitational force that is perpendicular to that. And that being perpendicular is what causes us to be pulled into a circle. And so that is simply a centripetal force, which is our force of gravity, which is going to equal mass times our centripetal acceleration. So we're going to take our acceleration we just solved for up here, and we'll multiply it by the mass of the Earth, which was a big number of 5.98 times 10 to the 24. So 5.98 times 10 to the 24 kilograms times 0.0059 meters per second squared. And I'm going to get a value of 3.56 times 10 to the 22 newtons. So a big force pulling on the Earth due to the sun. And remember, Newton's third law says that the Earth is pulling with the same force on the sun. However, the sun is so much more massive than the Earth that we have an acceleration due to that. And the sun, while it does wobble a little bit back and forth, has little influence on the motion of the sun as compared to the sun having the motion on the Earth. Okay, so pretty straightforward problem setup of just finding our speed, finding our acceleration, and then finding our force.